Where there's mass, there's charge. Where there's charge, there's electric field. Where there's electric field, there's voltage. Where there's voltage, there's electric potential energy. Mass has charge. All mass I know has got charge to it. Therefore, all mass is capable of separating charges. Once you separate charges, you create voltage. Voltage means electric potential energy. We define capacitance as the proportionality between charge and voltage. Thus, any mass or any object you like has capacitance because it has an ability to separate charge and therefore produce voltage or store charge separation and voltage. This is its capacitance. The flux capacitors banned are great capacitors actually because they have lots of mass, lots of charge, lots of ability to separate charge and have voltage across them, whether or not they're a good band, which I'm thinking they are just looking at them here. Ironically, this parallel plate capacitor over here towards the right, though we call it a capacitor, parallel plate capacitor, it most likely has a lot less capacitance than the flux capacitors. That's because it's got less mass, less ability to separate charge than all these charges over here. These are big charge systems over here, and typically a parallel plate capacitor is not so big, but it's easier to understand the capacitance of a parallel plate capacitor. And parallel plate capacitors are common in electric circuits, which also typically have capacitors in them to store charge and energy. So next, we're going to talk about capacitance in terms of parallel plate capacitors. Let's begin our introduction to capacitance by finding the capacitance of this parallel plate capacitor configuration as shown. The definition of capacitance is that it's charge divided by voltage. Okay, let's see. For the configuration shown, there's no voltage, and thus there's no charge on the plates. Because remember, we have to put up a voltage to get charge separation. So those two are directly related. And here we have none of them. What should we do? So in a case like this, it's a good idea to just go ahead and assume that there's some voltage between the plates and that a charge separation will come up associated with that, and see how we do. We assume a potential difference delta V, that is a change in voltage across the plates, which we're now going to start referring to just as Cap V, where it's understood that the Cap V refers to the voltage across the plates, which is just the difference in voltage provided by the battery. If you go back and look at our previous work, you'll find that we derived the fact that the change in potential, delta V, across the plates is equal to the electric field across the plates times the plate separation, which now we're just calling Cap V for change in voltage. Well, we see the distance D is given as 10 millimeters, so we've got that. What about the electric field? Well, we were given that before as 4 pi K Q, where Q is the charge, over A. We're given the area A, here is 400 millimeters squared, and the charge we know is the magnitude of the equal and opposite charge Q induced on the plates by the assumed voltage. Okay, so we're getting pretty close. Let's see if we're almost ready to try to figure out what the C is in terms of what we have. The capacitance C is defined to be the charge divided by the voltage that caused it, the charge separation over the voltage that caused it. Okay, well, what's the voltage that caused it? Well, okay, it's V, which is delta V, set one and the same. Alright, so it's going to be Q over V, which is also E times D. From our definition of the electric field, we have the electric field times D is 4 pi K Q D divided by A. So plugging that into the expression for the capacitance, C is equal to Q divided by 4 pi K Q D divided by A. The common term in the numerator and denominator, Q, cancels, and downstairs goes upstairs, so the A goes upstairs, and we get that the capacitance of the parallel plate capacitor is equal to the area divided by 4 pi K, K is the electric constant, times D is the plate separation. Notice that even though to derive it we assume some charge and some voltage on the plates, when everything came out in the wash in the end, the capacitance only depends on physical geometric quantities like the plate area and separation of the plates. And this is a commonality for all things capacitors, which are basically all things that have charge, can store charge separation, electric field, voltage, and thus have capacitance. And all these capacitors, everything that is, you, me, and this parallel plate capacitor and everything else is a capacitor, has capacitance that only depends on their physical geometric properties, not the actual charge separation and voltage that causes it. So the capacitance is, even though it's defined in terms of the charge separation per voltage that causes it, it's an independent geometric quantity, if you will, geometric physical quantity. Okay, moving on. The collection of physical constants, 1 over 4 pi K, is defined to be epsilon 0, known as the permittivity of free space, which has the value 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. So the capacitance can be more simply written in terms of this permittivity of free space constant as epsilon 0 A divided by D. Then putting in the numbers for our particular case over here, we got 400 times, I wrote millimeter squared as 10 to the minus 3 meters squared. Then our constant divided by the plate separation, 10 millimeters. And now our job is going to be to work out this mess right here. Crunching the numbers on my calculator, I got 3.54 times 10 to the minus 13. Let's see units here. I got the meters squared canceling with this meter squared. And now down I have this is downstairs upstairs. That goes downstairs, so that's going to be a Newton meter. And we were left with Coulomb squared times Newton meter. The units of our capacitance thus far then are coulombs. Let's see. Units of our capacitance are Coulomb squared over joules, because Newton meter is joules. Alright, let's see. That needs to be the units of charge over the units of volts. Okay, so that's got to be units of charge, which is coulombs, divided by the units of volts, which is joules per coulomb, right? Energy per charge, and that's equal to downstairs goes upstairs, coulomb squares over joules. Check. So we're good on the units. Last, let's just check that we're in agreement with PhET labs. So right now, here we have our parallel plate capacitor we just solved for the capacitance of. It's got no voltage on it, and thus no charge. But does it have capacitance? 0.35 times 10 to the minus 12 farads. Well, that's the numeric value we just found. And farads, well, that has to have units of coulomb squared per joules. So we're in agreement with PhET labs. Great. Does it depend on the voltage and the charge? Guess not. Not that way, not that way. Change the voltage to negative, it changes the polarity of the charge. No matter what we do, it doesn't affect the capacitance. That's because the capacitance is a property of the geometric and physical character of the capacitor. That is, its ability to store charge per voltage.